Projectiles, Part 1. Here are your priming questions. Let's start with a few examples of some different types of projectiles. In the first example over here on the left, we have an object that is just dropped, and this is usually what we call a free fall, so it's only going straight down. In the other example, in the one in the center, we have the object that is thrown upwards and then comes back down. And in the last example, it is thrown at an angle, and you can see more of the trajectory. And these are all different types of projectiles. What we need to keep in mind here is that projectiles are an application of what we understood for independent vectors. And by this, what we mean is that the only force that is acting on the projectile once it is in the air is gravity. And for this, we are going to ignore air resistance, which means that gravity is going to be the acceleration that we use. Okay, it only operates in the y-axis, and it is 9.8 meters per second squared going down. You'll need to memorize that. And because it's only operating in the y-axis, it has no influence on the horizontal variables. So the x and the y's will be completely separate in terms of their variables, except for time. Now, there are some new terms that you want to be familiar with for horizontal projectiles and just projectiles in general. So a projectile, object in free fall without any forces acting except gravity. Trajectory, this is going to be the path of the projectile. Typically, it's going to be parabolic. The range is the horizontal distance or displacement of the projectile. The hang time, this is going to be the amount of time spent in the air. And a term that you just need to really memorize is terminal velocity, and this is if we were to take air resistance into account. This is when the air resistance would equal the force due to gravity, and then downward velocity would not change. You can think of if you are jumping out of an airplane, you will reach a terminal velocity, and then when you have your parachute, you'll reach another terminal velocity. We can talk more about that in class. Now, because once it's in the air, only gravity is working on it, and the acceleration is 9.8 meters per second squared down, the horizontal velocity is constant. Remember, gravity does not influence it because they are independent. The vertical velocity will change due to gravity. So here we have a diagram. And here, let's say we have a cannonball, and in one case, it drops straight down. In another case, there is no gravity. And the other case is going to be the path that it actually takes. So this will be its trajectory, the projectile motion. And so with what we know here, what you want to think about is between these two, the one that is dropped straight down and the actual motion of the projectile, which one would hit the ground first? The cannonball that is simply dropped, or the one that is fired horizontally? And we will go through that more in class. Now, vector components. Once we have an object that is moving in both the x and the y, we can split up the velocities into the x and y components, similar to what we did before with our vectors. And so if you see here with a horizontal projectile, initially, it only has velocity in the x. It has 0 velocity in the y. But the moment it leaves and becomes a projectile, it begins to be accelerated downward and begins to accelerate downward, and so then it develops a velocity in the y. And what you should notice here is the x velocity remains the same throughout, but the y velocity gradually increases over time. And that's what you can see here. Now, this animated picture here is assuming a 10 meters per second squared acceleration, which is good enough for this example, but what you need to remember for us, for our calculations, we are using 9.8 meters per second squared. So let's go and give this a try. We are going to find the final horizontal velocity, we're going to find the hang time, final vertical velocity, then the final velocity, and then the range for this problem. So Legolas fires an arrow horizontally east with a velocity of 45.0 meters per second from a height of 1.70 meters above the ground. We want to find each of these. And so let's go and start by listing out our variables separately for the x and the y. And so if we start looking at this, it's fired horizontally so that we know our initial velocity is going to be 45.0 meters per second. Then we know that we are from a height of 1.70 meters above the ground, so that's going to be our y displacement is 1.70 meters. And what we are going to be using in terms of this is, if we write it out like this, what we have stated here is that down is going to be our positive direction because it's starting at 1.70 meters up, but it is only falling down in the vertical. So if that's going to be its displacement down, we're going to be using down as our positive direction. So that's all that's given to us at first. There are some things that we can infer from this list so far, though. It is only fired horizontally, which means that our initial y velocity is 0. And we can go and answer A. From what we've said before, the horizontal velocity doesn't change. So in this case, our v naught is equal to our v final, which is equal to our v average. And that's what that line across the top means. You can also write it out as AVG if you want for average. And so in this case, we know our final velocity in the horizontal is 45.0 meters per second east. And so these are going to be the same values. So we've already found A. Next, we need to look for the hang time. And for the hang time, we need to look at the variables that we are given, and we can go and put time on both because, remember, time is the only shared variable. And when you first look at this list, it doesn't look like we have enough information until you remember that we have acceleration in the y. So we know our acceleration in the y is 9.8 meters per second squared. And this is going down, which is going to be our positive. And so now we have our acceleration, our v naught, our d. We're looking for our time. And we have enough information in our y now to find our time. And so if you look at the variables here, we are missing our vf, which tells us which equation that we need to use. So in this case, we need to use, and we use a different color, d is equal to 1/2 a t squared plus v naught t. Now we know what our v naught is. It's 0, so this term goes away because that's going to be 0. So now we can work with this and plug in our values, and we know we have 1.7 is equal to 1/2 times 9.8 times time squared. And when you work this out, you should get your time is equal to 0.589 seconds. And that's what we get for our time. So that is going to be our hang time. And now for part C, we need to find the final vertical velocity. So that variable that was missing, we now need to find. So let's go and put this in. So we know that our time is now 0.589 seconds. And that's going to be for both the x and the y. So 0.589 seconds. And now we need to find our VF. And the easiest equation, not the only equation to use, is going to be VF is equal to V naught plus AT. Again, we know our V naught is 0, so we can cancel that out. So we know our VF is going to be equal to our acceleration, 9.8. And again, it's positive because, because we've set down as our positive direction. So it's 9.8 times our time of 0.589 seconds. So our VF is equal to 5.77 meters per second down. And that's our final vertical velocity. Remember, so right now we are only working in the y. So that's our final vertical velocity. And so now we're asked to find our final velocity. And when it says final velocity like this, what it means is the vertical and the horizontal added together, the resultant velocity. And so for this, we'll go and work up here. We know that we have our horizontal velocity going to the right. We also know that we have a vertical velocity going down. We know that this is 45 meters per second. We know that this is 5.77 meters per second. Remember, we add them head to tail. We draw a resultant tail of the first vector to the head of the last vector. And so now we simply need to use a squared plus b squared equals c squared. And we should get a hypotenuse of 45.4 meters per second. Now, this is only half of the answer in this case. Because we now have a non-perpendicular vector, we need to find the angle because this is a vector quantity. And so now we can use the inverse tangent. So we can use inverse tan. Going back to what we learned with our angles before, we use the inverse tangent of opposite over adjacent. So it's going to be 5.77 divided by 4.55. And that's going to give us our theta. And so now we know that our theta is equal to 7.31 degrees. And when we look at our measurement here, we are going south of east. So this would be south of east. So the final velocity here, we would write it out as 45.4 meters per second at 7.31 degrees south of east. And there we go. So we now have our final velocity. The last one is the range. And what we need to keep in mind is, going back to the definition, the range is the horizontal displacement. And so we need to work in the x. And we know that our average velocity is 45.0 meters per second. We know our time. And so we can actually use one of our earliest equations, v is equal to d over t. This equation simply relates velocity with displacement and time. And we can plug in and rearrange it to get to our d. And so we can now put in our values. 45 is equal to d over 0.589. So you can pretty clearly see that d is going to be equal to 45 times 0.589, which gives us a range of 26.5 meters. And that is our range going east. And that's it. And here are your primary questions again.